why I hate YouTube lectures. I do them, but I hate them. But YouTube lectures are still more palatable than a Zoom in my eyes. Okay, so the last part of class today, we're going to cover an example on Thevenin and Norton equivalent circuits. So the goal here is, how do we set them up? What does it mean? There are examples in the book, and I could just throw the book at you and be like, hey, go figure it out. But I like explaining things, which is weird. Okay, so I'm going to go ahead and draw not a terribly complex circuit. In fact, you know what? I'm going to go ahead and make this like this. So R1, R2, R3, R4. Okay, and then what we're going to do is we're going to go ahead and pull off two terminals here. So I have node 1, node 2, node 3, node 4. Okay, these are going to be the open circuit terminals that we're looking at. I'm going to go ahead and call this VA. Okay, we have our voltage source VS. We're going to say VS is equal to 10 volts. And we're going to say that all of the resistors are going to have a resistance of 50 ohms. Okay? And then the question is, how can you come up with both a Thevenin and a Norton equivalent circuit that has the same output as it would be if you were connecting a component across this open circuit? Okay? So that's the task. Now, if you remember, what we talked about extensively in the last lecture was that it has to have the same open circuit voltage, and it has to have the same short circuit current, which means we're going to have to analyze this circuit as if there was an infinite resistance resistor here, and if there was a zero resistance resistor there. Okay? An infinite resistance resistor, by the way, just kind of filters out. Act like it's not even, there's nothing there, which is not shocking because there is nothing there. It's almost as if nothing is a part of that circuit over there. Oh, because there's nothing there. So what we're going to do first is we need to figure out what the voltage is between nodes 2 and 3, because that is the voltage between A and B, or between A and B. VA to VB. So if we know what both 2 and 3 are, we can figure out what the open circuit voltage is, just as this is drawn. Let me know if you're struggling to see my handwriting, because I can write a lot bigger, or I get to use a different marker. Okay. So voltage 2 to 3 equals voltage A to B. Awesome. Well, we got to step through the circuit and figure that out. So we'll start by saying, okay, let's come up with, you could do node voltage analysis, you could do mesh current analysis, you can do a lot of things. I'm going to start by doing equivalent resistances and try to combine things, figure out what the current is through this loop. And once I know that current, then I'll figure out this voltage, and then I'll be done. I don't need to know anything else. Okay, sounds like a plan. So, we're going to take R2 and R3 and combine them in parallel, because they are equivalent in parallel. So, REQ1 is equal to 1 divided by 1 over R2, so 1 over R3. Since both of them are 50 ohms, shockingly, REQ1 comes out to be 25 ohms. I don't even want to do the math there. I don't have to. That's just how it is. Okay, so now we can take this circuit and simplify it like this, where this is 25 ohms because it's the REQ1. This is R1 and this is R4. And here's your voltage source. Okay, all three of those resistors can combine in series because they're all in series to form REQ2. And that's equal to R1 plus R4 plus REQ1, which, by the way, equals 125. Again, quick maths. 50 plus 50 plus 25. So now we have a circuit with just a power supply and one resistor. If I know what the current through that resistor is, I know what the current coming out of the battery is, which means I know what the current going through this is. Really, because this is node 2 and node 3, if I can find the voltage across REQ1, I have the voltage between 2 and 3, voltage 2 to 3, which is equal to voltage A to B, because A and 2 happen to be on the same node. B and 3 happen to be on the same node. If I can figure those out, I'm good. We're in a good place. We're done. So, 125 ohms. We've got 10 volts. So Vs, REQ2. We know Is is going to be Vs over REQ2, which is equal to 10 divided by 125. I cannot do that in my head. Well, I mean, I probably could, I just don't want to. It's 0.08. Amps. Okay, so that means we know that the current coming out of this source, Is, is equal to 0.08 amps in this configuration. Okay, which also means we know over here, the current coming out of this source is equal to Is, which is equal to 0.08 amps, which is the same current that goes through here, here, and here, because there's only one loop. So we have 0.08 amps coming out of the source voltage. We have 0.08 amps going through REQ1. All we need to know is the voltage across REQ1. So V REQ1 is equal to Is times REQ1. REQ1 is 25. Is is 0.08. 25 times 0.08 should be equal to 2 volts. And that's the winner chicken dinner. Okay, now we know 2 volts. In this configuration, the open circuit voltage, which is the voltage between 2 and 3, which is the voltage between A and B, which is VA, is equal to 2 volts. Well, VA to B. Okay, so gonna go ahead and write that down. I'm gonna call it VOC equals 2 volts. Stands for V open circuit. Now we have to do all this math again in a short circuit configuration. Shouldn't erase that part. All right, in a short circuit configuration, you short A to B with a single wire. How much voltage is between A and B when it's shorted? What? It's 0, yes. Because in a short circuit configuration, there is current, but there's no voltage. So there's no voltage difference between any part of this wire. And that goes along with our understanding of nodes. A node is anything that can be connected without having to go through another component. By connecting these with a short circuit, we have merged 3 and 2. 3 and 2 have to be at the same voltage now. Okay? Which means there is no current going through R2 or R3 anymore. It is entirely going through that side of the loop. So R2 and R3, we can completely ignore them now and draw the same circuit that looks like this. The short circuit one's always an easier calculation, which is pretty awesome. So here, all I want to do is I want to find the current going through this loop. So if I find the equivalent resistance, I can find the current going through that equivalent resistance, and that's my answer. That's it. One step, one calculation. So REQ1 is equal to R1 plus R4, because these are both in series, which is equal to 100 ohms. Okay, so we've now come up with a new circuit that looks like this. Okay, the amount of current that's going through there is equal to IS is equal to VS over REQ1 is equal to 10 divided by 100 is equal to 0.1 amps. And that is our short circuit current. So VOC equals 2 volts. ISC, or I short circuit, between A and B is equal to 0.1 amps. We now know everything we need to know to create a Tavenon or a Norton equivalent circuit. Okay? So, I'll draw both of them just for fun. Here's our Tavenon equivalent circuit. Here's our Norton equivalent circuit. So the question is, what is VT? Do you have any guesses? It is equal to the 2 volts, because if we don't put anything across here, we have to have the same voltage here as we have here. And what we calculated was, with nothing across these 2 terminals, there's 2 volts here. Well, with nothing across these 2 terminals, there's no voltage in the Tavenon equivalent resistance. So this should also be 2 volts. So we know VT is equal to 2 volts. What is RT? We'll have to do a little bit of math. Okay? What is IT over here? It's 0.1 amps. Because we know if we were to short these 2 ends, just like shorting these 2 ends, we should expect the same amount of current traveling through the wire here as traveling through the wire here. Now, all of the current is going to go through the wire when it's shorted, just like all of the voltage went through the open circuit when it was open. So here, your I Tavenon is equal to 0.1 amp. Now we do have that RT that is just kind of floating there. RT is what brings these 2 circuits together. If we short this here, we would expect the amount of current to be traveling through that wire to be equal to IT, right? Because that's the same over here. If we short it over here, we expect the amount of current traveling through that wire to be equal to IT. So since we know the amount of current traveling through this wire is equal to IT, the amount of current traveling through this wire should also be IT, through that resistor. So RT here is going to be equal to VT divided by IT. Now we can also go on this side. The open circuit voltage here is equal to the amount of voltage that is generated by current flowing through this resistor. If all of the current is flowing through that resistor, there should be 2 volts across those terminals. Well, so the equation you get here using this one is that RT is equal to VT divided by IT. This happens to be the same equation. It's the same resistance, so it makes sense. So really all you have to do is just divide this by this, and you get this, and this. So 2 divided by 0.1 is equal to 20, which means the Tavenon equivalent resistance is 20 ohms. Which means this equals 2, this equals 20. This equals 0.1, this equals 20. And we've come up with our equivalent circuit. We can plug absolutely anything in between these 2 terminals and figure out what the behavior of that system is without having to step back and go to the original equation. Now you'll notice, what's the difference between Thevenin and Vs? Which one is bigger? Vs is larger. Why is Thevenin smaller than Vs? Because there's power in the original circuit, there's power being consumed elsewhere. And that power being consumed elsewhere can be modeled as this. Now this isn't equal to the amount of power that's being consumed elsewhere in the circuit. But it's being modeled with that, but that's the reason why VT is going to be smaller. We don't have as much power being supplied to this terminal because there is a rest of the circuit that has to consume power as well. Similarly with IT, the current that is flowing through R1, unless you're shorting this terminal, the current flowing through R1 is always going to be greater than the current flowing here to here. And the reason for that being that you have current that would be being diverted to other branches in this circuit. So just a fun bit of math to play around with. Let's do one other quick example before we go. And I say quick because this is going to be really fast. Okay, let's say we just have a very simple circuit. Okay, you got your Vs, R1, R2. We're going to go ahead and pull our nodes A and B out here. Okay, we'll go ahead and label the nodes. This is 1, this is 2, this is 3, this is 4. Now, the question I have for you is, what is that open circuit voltage? I don't even need to give you values for anything else. What is the value of the open circuit voltage? Yeah, give me an equation. Sure. What is the voltage between 2 nodes that are connected with a short? It's 0. So here, VA to B is equal to 0, and we know that, which means our Tavenon equivalent resistance equation for this, unfortunately, you're not going to, you can plug in any component here, you will never get power out. because it's already shorted. So that is something that you have to consider when you're doing these equations. It's not just simply like, oh, well, we plug something in, we get stuff out. Like, no, there are places you can plug into the system where you don't get any power out. It's impossible because you have voltage. These are the same voltage level, the same energy level. You can have an electron travel through a circuit and end up at the same energy level if it loses energy anywhere else. So this is a no power system. And that's why I said it was going to be simple. A Tavenon equivalent circuit for that would just be it'd be a voltage and a current source equal to 0, which is kind of useless to draw. Okay, you will have homework due Tuesday. You'll have a reading assignment due, which I believe the reading assignment is watching a video for next week, because we're doing Pi stuff next week. But you will have a homework assignment due, and those are book problems. So it'll be due at the end of the day on Tuesday. Ask questions. On Tuesday, if you have a Pi, bring it. I'll show you how to hook it up. I'll show you how to wire it. We'll start playing around with stuff. On Thursday, we will code a very simple program to make light flash. That's it.